Hello again. This is Al, and welcome back to this tutorial series, lesson number 37, where we're currently looking at the concept of a linked list in C. We're not at C++ yet. And before going on, as you can see right away, I've added some extra functions in here. I want to point out a few things from the last time that have changed. This in the last lesson was called add node, I believe, and I renamed that now to add tail. That means it adds to the tail of the list. You still have that picture? No. But if our linked list had a bunch of nodes, recall the picture. Hang on a sec. As I was saying before being interrupted by my computer, which will probably interrupt me again, what was I saying about the nodes? Oh yes, heads or tails. If you think of the nodes, as I said, gotta be careful because if I press enter at the wrong time, it's gonna get me. No matter what the order in memory of these nodes is, as far as we're concerned, they have a certain order, 1, 2, 3, and 4, and so on. And perhaps if the fourth or the last one, then there would be a no. Now, we can either add a new node at this position. This would be the tail. Tail node is node 4, or we can add a new node somewhere else and shift all the numbers down. So we could add this here in front of the head node. We could swap out the head node with a new node and then shift everything down one. Okay? So what we've been doing is adding to the tail, and that's why I renamed this to tail. Now, that's unimportant. That's just a name change. The more important bit was something that was picked up by the compiler, and I hadn't noticed because I was working on the other file, and that is that I had a const qualifier here, and also here it is. How many times I've pressed this, I don't know. Don't show this message again. Yes, don't show it again, please. Excuse me. In the header file, I had the same thing. So it wasn't particularly noisy about the warnings. Here, different const qualifiers. Now, at first when I looked at this, I thought, well, I'm not modifying pnode in any way. I'm not changing the data. And all I want to do is indicate this function doesn't modify the value of what's pointed at by p-node. But in fact, the compiler's description of this warning makes perfect sense and indicates to me that what I've written here is in fact an error. Not a warning, but it should be an error. And in C++, this is an error. This code would not compile if this were a C++ file for a very good reason. That reason is described here in the help. That'll never load up. You can hear the music of Jeopardy sounding. Where'd it go? Oh, here it is again. Okay. Variable used in an operation is defined with a modifier, const in this case, that prevents it from being modified without detection by the compiler. An operation is being defined with a specified modifier that prevents it from being modified. So this is like a double negative. Prevents it from being modified without detection. So it is allowing it to be modified without detection. Maybe the example will help clarify. Const q. Basically, if you if you run through this, I know what it's saying. Basically, what I'm doing here, it's quite obvious what I'm doing, which is I'm fooling the compiler by storing this unmodified variable into a place in memory, which does allow modification of its members. So although I'm not modifying p-node, I'm hiding it inside this object, which allows modification because as far as its declaration is concerned, its members can be modified. So this is really an error, and this can't be declared as const, even though I'm not modifying it. Same in the header file, not const. So that's important, and also important in a successor language like C++, that it disallows such types of trickery. Now, they could have added that feature to C. I'm not sure exactly why you're allowed to pretty much do anything in C. You can lie and do all sorts of things, but in C++, no. I guess because C++ is the successor. Okay, so I've added these extra functions. I told you about this tail. This one adds to the head of our node, as I said, of our linked list. And there's one to get the count of the number of elements, and so on. So in main here, I've defined two lists, and I'm going to take the same argvs, and in one list I'm going to add them to the head of the list in each iteration through the loop, and in the second loop adding to the tail. This is the one we've seen already. This is the new one. So maybe I'll switch the order of these. This is what we've seen. And this is the new. Okay, so that means I can just sort of skip past this part but I won't for the first couple iterations. Alright, let's have to build it. Oh, by the way, you'll notice there's that thing, alloc node here. When I press F11 on this, now it's taking me to the right spot. Before, it didn't. And sometimes that can happen, and there's a way to fix that. And to fix that is simply exit the Dev Studio and just delete this NCB IntelliSense database file and start it up again, and it should resync and get everything back going again. That file can often get corrupted, often does get corrupted. Okay, so these are both known. Now, here in the watch window, I have pretty much all the things of concern to us. Our node, the string pointed to by our node, and the two lists. Now we're working on the tails list. The first step through add tail we've seen, that's going to should replace the tails list with the value of P node. So this should become exactly 3E59B0. And there it is. The next time through, now I've made a new node, but adding to the tails list should not modify this, so it won't go red. And it went red, but it's still the same value. I guess because some of the data changed. The next change. The next time, I don't think it'll go red. Shouldn't. When something goes red, that means something was modified. Yeah, no red. We're far away now, far enough away that we won't see any more changes than that. Okay, now onto the new. Now I'm allocating new nodes. I can't take these same nodes, by the way, and add them to this list, and for a fairly obvious reason. But I won't explain that just yet, or maybe I'll leave that as a puzzle. Okay, now here's our new node. Now I'm going to add it to the list, add it to the head of this list. To do that, I simply take the node passed in and set its next pointer equal to what's pointed at by the list value. That is, I'm making this now the head of the list. And the next pointer will be what was the list. This is currently null. So now I've set this guy's next to point here, which is a value in memory. But this is an address in memory, but its value is null. Now I'm going to set that equal to something. I'm going to set it equal to the node. So now, plist, we'll step out here, has an element in it. And you're going to notice that every time through this loop, the heads list here is going to change the values. Because as we add to the head, we're always changing the head of the list, so we have to update the pointer to the list. Okay, next, print them out. First, I'm going to print the list that we added by tails. That's the old way that you saw before. And I'm using this thing to count the number of elements, which goes in here. And in fact, I didn't need to make a new variable here. I could have used plist to do this walk. And all I'm doing is going through until the next is equal to null, each time incrementing some count. So we start out at the head of the list. It's not null, so we will increment, this count will increment once at least. Now I'm getting the next for the first node. It's not null, increment the count, and so on. And end count ended up being 6. Here's the printout, tails list. Print list is the same as before. And that's the list we saw before. Now, same thing for the heads list. Also 6 items. But as you may have guessed, this time in reverse order. So that's the result. 2 lists, one in one order, one in the opposite order. One using one method of insertion, another a different method. Okay, now there are several things to be said about this. Okay, as I said, there are several obvious problems with a lot of this. I've made a list of them, some things I could think of anyway. One of them is scoping. These here lists, which I've given the names list heads, list tails, are declared within the scope of this particular function, main. Now, well, it's lucky that main is our entry point, so we're never going to lose sight of these. But if it were in another function, and we return from that function, we would lose our only reference to all these nodes we've been allocating, and in fact, that we haven't been freeing. This program has a memory leak. In fact, I can show you how to see that memory leak. Just hang on a sec. I need to gather something from somewhere else. Okay, just wanted to find that function. You include this CRT debug header file and call this at program startup. Then when your program ends, you'll see it already. Whoops, let me show you. Here's the program, in the program, and it says detected memory leaks. Here they are here. 1, 2, 3, should be 12 blocks. Okay. Now that's obviously not a good thing. We're supposed to be freeing the memory that we've allocated. In our case, it's nothing critical. It's just a few bytes. But a memory leak in general could indicate another type of problem, something mismatched, something out of line, something that needs to be addressed. And so that's another issue with, at least with what we have here. I'm going to leave that off. I'm not going to worry about that right now. What else now? Yeah, now hiding the data, the node, this node object is kind of out in the open. You see, we shouldn't really have, we as meaning the person using this linked list node manager, shouldn't really have any access to this, in particular, this piece of data. we have to allocate nodes in order to add them to the list. We can do things that are definitely wrong, given the fact that we can modify these things directly. Now you might think, okay, yeah, but it's my list, I can do whatever I want with it. But remember, if you're working in a company or something, people don't know, might not know what they're allowed to and what they're not allowed to touch, and they might do something like, I made an example here. This is in the heads. In the heads, no. What I'm saying now, if we're on the last iteration through this loop, I'm going to take the next node, the current node, it should be this one. Tails. Okay, now does that make sense? In the last, so suppose I is equal to argc minus 1, which means this is going to fail on the next go. The current node that I just added, his next will be null, right? Because I just added it on the end. So the current p node here is the last node. If I set his next node equal to the head of the list, I will have created a circle. Basically, this loop, the loop to print this out, would go on forever. I'll just show you that happening. This would ever start. Alright. Well, everything so far so good. Here's our list. It's moving along. Now, on the last node, here's our list. It stops. Not at the last one yet. Okay, now before I do this, let's just go and look at our list. We have 6 elements. Right, and then it stops. But now, I've set the next node, of the last node back to the beginning. So here's our list tails now. You see? It's just going to go on and on forever. If we try to print this list out, it's just going to wrap and wrap around and never get to the end. In fact, if I just run this, you'll see what happens. Well, it doesn't even print. I would have thought it would keep scrolling, or maybe it is. But anyway, we had to kill it by just killing the program. Okay. Because it couldn't get the count. That's why. If I'd taken this out, you should see it print forever. It's incredibly slow for some reason. Turn you off. Make sure I said go. There we go. See, it's going to print forever. So that's not a good thing. We shouldn't be able to do that sort of thing. And some other examples here. maybe that's just enough for examples of bad things. I haven't shown you removing a node. Maybe I should do that. These are some experiments I had set up. So I defined two nodes. Maybe I can just do this quickly. What I want to do is remove the second node from each of the lists. See what we get. So node 2 from the heads list and node 2 from the tails list I've defined here. And then in both cases, when I is equal to 1, how am I doing that, I wonder? Oh, I'm setting them. Okay. So yeah, I need one of these here. This is the head, this is the tails. You go there, and you go here. So I'm just keeping track of the second node in both of these cases, so that I can just show you how the removal works. Now, a bunch of experiments. Okay, so first, let me just remove from the heads list the recorded P node 2 heads and see what we get. That's the second list printed. Okay, so the second element, which would have been the word this, which was here, got removed. Now how does that remove work? The way that works is basically I walk through the list until I find a node whose next node is actually equal to node, or there's no or at the end of the list. So if these become equal, the loop quits, and if there is a next node, what I'm doing is setting the next node of this node to be the next node of the node passed in. So in our picture, if I want to remove this node 2, if I want to get rid of this, that means that if I find, well, it'll be on the first node, I find that node 1's next is equal to the one I want to remove. So what I've got to do is set node 1's next equal to the passed in one's next. So I gotta make this equal to a 3. And who knows what happens with this guy. Still out there in space somewhere. But now this one is going to go from 1 to 3 and 4 and so on. So that's how this test works. This comparison is checking whether the next node for the current one I'm looking at is equal to the node I want to remove. And if I find such a node, I'm going to set this new next node equal to the next of the node passed in, which might also be null if it were the last one. And you'll notice also that if I try to remove from the heads list something from the tails list, it should have no effect because those objects are not usually in that list. So it's the same. This this list was not affected. Okay. Similarly, I can remove something from if I remove the second element from the tails list, I'm printing this out twice, aren't I? Print list and print list. Let me do it just one print out. Okay. Now you notice that I've removed the second element from both of those lists, and in fact, it's the same element that disappeared. Because of the way these lists are organized, when I walk through this one, when I added the 1th element to this one, it was the same argv value as for this one. So although I'm calling this node the second node, in fact it's not the second node in the reversed list, it's the second to last node. That's just a matter of wording. Okay, what else is wrong with this? No data hiding. Make a circular list. We can't add the same node to two lists. That's okay. Impossible to tell which list a node belongs to. That's true as well, by the way. There's no real way to tell. Suppose I had a node and I wanted to remove it from either the heads list or the tails list. How would I know which list it belongs to? The answer is you can't really tell except by walking through both lists and seeing which one you might find it in, and that's a slow operation. Now, that doesn't mean we have to invent C++. We could handle most of these problems in C by taking all that node functionality and making it kind of private, make them static inside of another C file, and then we could make a manager type set of functions that manages the nodes for the various lists. And the way these things usually work, like in Windows or whatever, this thing will just return pointers to void for the objects that you use to reference things with. And only it knows the format of whatever the data is inside this p void. So if you would call some function, create list, it returns you a p void, and usually you call this a handle. Okay, that's where the word hwind comes from, handle to window. That's because Windows is hiding the data structure's internal workings from you so that you don't go and mess it up incorrectly. Now, in order to add items to your handle to list, you pass the handle value to the manager. The manager can use the information it knows in order to add or retrieve data from the list, and also to create a new item. You pass in the list, and it would return you a p void, a handle to your node a reference to your node. So you could use this as like h node. You could have something that returned a handle to a node, and in that node handle, it could maintain information about which list it belongs to, where to find it if you want to delete it or something. If you want to delete anything from its list, it knows which list it belongs to and whatever. So like I said here, it can give each list a unique identifier from which to refer, and it can place that identifier in some kind of struct that's contained in the node value given to you for you to reference your objects from the list. If you want to walk all the objects in a list, you could use this manager thing to say, please retrieve the first item, the next item, and so on for this list handle. And so this is sort of the standard way this kind of problem is dealt with in C. Not in C++, but we'll get to that. Okay, now for the next lesson after this, I'm going to go to a simpler data structure, the string, regular C string, and look at the kinds of operations we do on strings and see if maybe we can actually start talking about C++ in that context. This context is a little bit too advanced to go to right away in terms of C++, I think. Okay, so we'll see then.